Hello, everyone. They say that you're supposed to let people see what you look like, so here I am. I will add some disclaimers. This is a discussion about a device that is flying around. There's always a chance with flying devices that you might lose control of it, and then it runs into somebody and hurts them. So my advice is do not create a physically real version of this device. Because it's too dangerous. Unless, first of all, you have the legal permission to do so, and you have the equipment and the land and the facilities and the training and the experience and a safety program and a desire to have this physically real device behave itself in a manner that is safe and legal and reasonable. Disclaimer number 2, I do not have the financial structure to create a physically real version of this device. There are companies who I'm sure would be happy to create it for you. You just tell them that you want one and they will see the specifications and can tell you what their price would be to create it for you. There is a company that makes prototypes and has told me that it's okay with them for me to put their name out for people to look at, so I will show you that and you can contact them. I assume they might make one or they might make many, I don't know. All right, and here is this person. This is just straight out of LinkedIn, ZTL Tech. I do have SketchUp drawing files that you can take the SketchUp Pro 2021 drawing files and open them in your version of SketchUp and then save them as STL files or whatever 3D format this company would like in order for them to give you a quote about what their charge is to create any of these items for you. Disclaimer number 3, I spent a large part of my career explaining scientific concepts to people who did not have a lot of scientific training. And these concepts were frequently very important and very significant and a little bit anxiety provoking or concerning. And so I learned that in order to explain things to people, you need to talk slowly, you need to use normal words instead of jargon. I've discovered that you need to repeat yourself 2 or 3 times, particularly when you're explaining stuff to people that they're not very familiar with. It seems to me, my discovery, somewhere around the 3rd time you say something to people, they begin to understand what you're saying. But for people who are scientifically well-trained and knowledgeable about what I'm talking about, that can be unbelievably boring. So all I would say is, if you're at parts of this video that you already know about and it's boring, just skip it. You don't have to watch it. Most of this is really entertainment only. All right, let's start a video. All right. Well, hello everybody. We're looking at the Smart Mortar. This is inside of SketchUp Pro 2021. This mortar is made using one of the standard airfoils. It is the AH80136 airfoil. And this flying device has been made inside of a aeronautical program that can give information about the device. It's 4.16 feet long, and it's about 33 inches wide. Thickness wise, it's about 7 to 9 inches. This right here I'm showing is just the mortar, a Smart Mortar itself, with nothing inside of it. You can see that these are holes cut into it. Here's a hole right here and a hole right there. And we can actually select this top piece and hide it if we want to, and you can look around inside of there. So there you go. These are other views of that mortar, showing that actually inside of the mortar are parts, and these parts include ailerons that can affect the flying of the mortar. Because of the nose pitch down effect of airfoils that have camber, there's an aileron or a flap in the back that acts to keep the mortar from flipping over as it flies. So use of these ailerons gives you the ability to control, independently control the pitch of the Smart Mortar. You can also independently control the roll of the Smart Mortar. And these two ailerons right here, because of how they're located kind of upwards and flat onto the edge of the back of the Smart Mortar, they give you the ability to control the yaw. So this flying device has all of the properties of a normal flying airplane: pitch, roll, and yaw. The aeronautical program says that if you, the weight of the structure itself is about 21 pounds for the skin. The skin is thick enough that it acts as the airframe structural member. Inside of the mortar is the payload. The payload weighs 12 pounds. I've already discussed what the payload is with respect to a military device. You can take, again, we can take this top half of the mortar and hide it. So here's the payload. Here are these ailerons. There's the flap that controls the nose pitch over. Of interest, there is also in this flying device two fans. These fans can go in either direction. This fan can spin in a direction where it suctions air out of this part, this opening in the Smart Mortar, and takes that air and suctions it out of there and blows it out of this side, so that the effect, and there's two different fans, and so the effects of these fans is that if the Smart Mortar manages, either by hitting a headwind or maneuvering to get itself into an airspeed where its flight control surfaces do not have enough size to control its flight, then it can actually spin up these fans and blow air to give the ability to do a pitch, roll, and yaw, because some of the air is diverted back here. So it can do pitch, roll, and yaw even if it's flying so slowly that the flight control surfaces are too small to have an effect on it. And if this Smart Mortar is pointed straight up and given an initial airspeed of 888 feet per second, then it will go, and if you keep it flying at a very slightly negative angle of attack so it has no lift, then it will fly in a straight line and fly straight up. And if it flies straight up based on the aeronautical calculation package, it will fly straight up for 15 seconds. At the end of 15 seconds, its airspeed will be 163 feet per second, which is 111 miles per hour, which is 100 knots. At that point, the flight control surfaces can bring the Smart Mortar into a nose pitch down activity, which causes it to go from vertical flight to horizontal flight. And at this point, it will be flying horizontally at 163 feet per second. The altitude will be 7,400 feet. The glide angle will be 8.57. So at this point, the Smart Mortar will be 7,400 feet in the air, flying in a slight decrease angle of flight. It's not horizontal flight, it's it will fly 8.57 feet horizontally for every 1 foot that it drops in altitude. And this can all be demonstrated with the aeronautical program. And the question that comes out of this is, well, all right, but what does all of this mean? And that's the next thing that we're going to get into. All right, well, I thought I better do a little bit more discussion of how these ailerons control the flying of this device. This will be very brief. It's really, this discussion is for people who already understand aircraft. Most of the time, for example, the ailerons that control roll are on the backside of this surface, but this Smart Mortar is configured where it can fly using its ailerons when it's going really fast, that is a high airspeed, but it also has the ability to fly using these fans when it's going slow. Either it's going slow because it got itself into a condition where it's going slow, or it hit a headwind, and suddenly the ailerons, which are completely adequate for high speed, 800 feet per second, 700 feet per second, 200 feet per second flying, they're not adequate to control it at low speeds. And once you decide you're going to do that, it changes how everything is positioned. But these are just standard ailerons in the sense that, for example, if you wanted to do a roll where the right wing went up and the left wing went down, then what you would do is you would extend this aileron so that it generated an upward force on this wing, and you would leave this aileron flat, but you would extend this upper aileron. And so you have a downward force pushing down on the left side, or the left wing, and you have an upward force pushing up on the right wing, and it rolls it to the left. This is very basic aeronautics. Yaw, obviously, if this one extended and that one didn't, it would generate a push that would tend to yaw the flying device off towards the right. Finally, because of the camber of normal airfoils, there's a tendency for the entire any flying airfoil to pitch over. And that's just a feature of camber. Most airplanes have a tail, but this one, because it's going to be launched at very high speed out of a pneumatic cannon, it has to have a shape that would allow that. And so this is all tucked down and flat in the back of the flying device during the launch phase. As soon as it clears the pneumatic cannon, this begins to extend and acts to counteract the nose pitch down effect of a airfoil with camber. And so all of these ailerons here, 1, 2, 3, 4, and there's 2 more on the bottom. All of those are exactly the same. The central flap aileron is different, and we're looking at these 6. They're all exactly the same. And what I'm showing here is the mechanism for how does this work. I have picked off of the internet a little drawing of, and these are available on the internet for $3 a piece. And here's your size. It's just nothing more than a gear motor. And what I did is, remember, this is a device. This payload has 4.5 pounds of C4 in it and other payload features to affect the way that it acts as an explosive ordnance. All of that is discussed elsewhere. So this whole device is going to wind up not existing anymore when it gets to its target. So you don't want to make $50,000 components inside of this thing. So, and also there may be an argument. Someone might say, well, I don't think that's where the aileron should be. I think it should be over there, or it should be over there, it should be over there. And so I made them where they're all separate and you can move them around and get them wherever you want to put them. All I'm demonstrating here is their normal method of working, and the gear motor generates through the gears a torque, and the torque is increased and can turn this gear here. When this gear here turns, it turns this horizontally oriented gear, and when that horizontally oriented gear turns, it moves this. These are dual 2-track ball bearing spherical bearings. There's a bolt here. These are just markers so I can move it around without getting confused, but in the real device they're not going to be there. But this would turn, that would go back. There is some structures here on the on this plate to control and force it to move where it's supposed to. You can see, remember that we want this aileron to be able to adjust itself in a manner where you can take air from the fans and blow air through that opening. So you have to have a condition for the aileron where it can get itself where the aileron is not in there at all. It's not in the way. So it's in this condition, it's moved all the way back. And then as this motor turns, this gear turns, that gear turns, this goes forward, and we're closing off this opening. And then at this point, this indexes up and sits nice and flat, because one of the aileron requirements is that it protects the interior of the flying device during the cannon launch and can act as a protection for it during the high airspeed flying. And you can see here that there are ways that this aileron can move itself and adjust its angle in a manner where it never really opens up the interior of the flying device to the high speed air. And this angle is about maximum 7 to 8 degrees of angle of attack, which is more than enough angle of attack to control the flight of this thing when it's going 800, 600, 500 feet per second. As it slows down with further advancement of this motion arm, this thing can extend to give you even more angle of attack, to give you control of the flying device at low air speeds. And so that's it. That's just the aileron that controls yaw, pitch, and roll. The other flying part that we'll discuss briefly is the central flap in the back that prevents the airfoil shape of the Smart Mortar from doing a nose pitch down rollover, and that's just showing that this is another airfoil. Again, here's the little gear motor that controls it, and it is slightly different from the other ailerons in the sense that this one does not have any air that's blown up through it, so it doesn't have any use at extremely low speeds where you would vent air to it. It's not needed. It's really for the high speed stuff. And you can see that when the Smart Mortar is launched and it's going through the pneumatic cannon barrel at 800 feet per second, this flattens itself down and is held in place by the strength of these connections. And there's also a little set of wheels here. We can get more details, but when this is all locked in place, this thing is held down and it can't go anywhere. And it stays like that until the Smart Mortar exits the cannon barrel. Then again, it's the same operating principle as before. This gear motor turns on, this gear turns, it rotates this, it pushes that back. And what happens is it lifts up this, first it lifts it up so that it can be like the tail of a flying plane. And it has a little bit of a negative angle of attack, so it pushes down on the back end of the Smart Mortar so that the Smart Mortar loses its tendency to a nose pitch down flip over. And again, remembering that all of these parts, I think, perhaps with respect, maybe not needing, other than these spherical ball bearings, it could be all of this could be made of plastic. These shafts probably need to be alloy stainless steel. That would have enough strength to control it. Remembering that this Smart Mortar is going to disappear and not exist anymore when it completes its mission. So we do not want a $20,000 central flap either. All right, a little bit more discussion. This is just a really pretty version done with a rendering program showing how this fan can take air from this aileron to that aileron, or it can take air from this aileron to that aileron, so depending on how it rotates. And we've discussed the principles of the Smart Mortar in more detail elsewhere. It needs to be inexpensive, where a small outpost could use it, where they could bring the explosive power of this payload against enemy forces. This would be inexpensive enough that the higher level commands would not care if they use it or not. And they would have 200 or 300 of them. They would have their own air force. It would have a targeting accuracy of plus or minus 2 feet inside of its range of 4 miles. So they could create an 8-mile diameter circle where they could drop one of these or 5 of these or 12 of these wherever they wanted to, whenever they wanted to, fly through the air and not make a sound. And you would probably hear the pneumatic cannon launch it if you were close enough. But if you were 1, 2, 3 miles away or 4 miles, you wouldn't even hear the cannon launch it. And I wanted it to be a weapon device of a type where the enemy forces would just simply say, we don't want to mess with these people with this thing. I just switched it to a more magnified view. But anyway, the enemy forces would say, look, let's just forget it. If these guys have this 4 mile radius, 8-mile diameter circle where they have this thing, just let them have it. We don't want that property. It's not worth it. All they do is they bomb us. And they bomb us all the time with this thing, and there's nothing we can do about it. That was the point of the Smart Mortar. And I think it needs to be inexpensive, or they will never get permission to use it. And that means I think it needs to not have a motor, because it doesn't have to have a motor. It doesn't have to have a propeller. It doesn't have to have thrust. It doesn't have to have fuel. It doesn't have to have all of the complexity associated with powered flight. And the problem that comes up is if you keep it at 800 feet per second, which is less than the speed of sound, it only goes up 7,400 feet before it can't go any higher, because it will be at an airspeed that's too low for a decent gliding angle. And I was very nervous that, this is such a great little thing, except it's at 7,000 feet. They're going to see it and simply shoot it. And I thought, well, I think I better, I just was wondering, how hard would it be to shoot this thing anyway? And as I was considering them shooting at it, I began to have a thought process of, well, what is involved in this thing flying around and they're shooting at it and it becomes a failure? as a defensive weapon, as a weapon that tends to push people towards negotiation instead of war, because while it's got great capabilities, they can just shoot it down. And I thought, well, maybe I'll look at it a little bit and work through this. And I decided I would make a big one, and I put my little robots inside of it. I was just enjoying myself and having some fun. But I did do a kind of a photo shoot with it up in the mountains, flying along over this road. And I began to work through the issues associated with, okay, it's there, it's in the air, they can shoot at it. Is this really a failure? And again, this was really just to have some fun. It's not, this would be a gigantic mortar. I had a few of my little mannequins that I put inside of it. This guy here, he's kind of looking at the flight controls, and I was going to tell the story that a group of them said, well, we're not flying around in this thing if we can't see where we're going. So up here in the front of it, I put some windows, and you can see them as it's flying. They decided to do a low pass over this road, and I have them in there in the front of it looking through the window. Anyway, let's go look at the issue of visibility. All right, before we get to visibility, there's one other thing we should talk about. Here we've got them, they're flying off the mountain on their way to somewhere, and they've launched one, and he's kind of been loitering a little bit, so that the cannon construction is probably going to be able to launch about once every 30 seconds, maybe every 40 seconds. So when you launch this one, if you want them to come in and land on the target, bang, bang, this guy kind of has to loiter a little bit so this one can catch up. And I wanted to bring out the understanding that there is space in here. You saw all those parts, but there's space in there, and you need flight control. Flight control is going to need a microelectronic solid state circuitry of probably drill a hole here and a hole here, and let the device itself be a pitot tube so you can get altitude and airspeed. There'll be a GPS in there so it knows where it is. There'll be an incline measuring device to measure inclination of the device in all three axes. I think it probably needs a solid state gyroscope, and probably a solid state compass and a solid state altimeter, plus a central processing unit, plus memory, so that you can load flight control programs to fly it. It is my opinion, that sounds like ha, but I believe you could get all of those parts in a item the size of a deck of playing cards, easy, with Intel and their 14 micron synthetic die size right now. I think it would be shocking how small you could make that package. And remember, all you have to control is 7 gear motors, and the gear motors need to know on versus off, forward rotation versus backward rotation, and speed of rotation. That's it. That's the only outputs you have to have. And there's just a couple of batteries in there. There's batteries to run that gear motor, and also the sensory system and the processing, and to run those fans if they're needed. I don't think this is a fighter plane that's doing loop-de-loops and barrel rolls and flying up and down and around and behind it. That's not what it's put together for. It goes up in the air and it flies to its target. When it gets to its target, it points its nose down and hits the target. So it needs to be able to fly. Most of its flying capacity is structured so that when it leaves the cannon and gets to its flying altitude, it can be brought to the target with reliability and accuracy. And we have to work ourselves through Yeah, right. But this is great, except for one thing. Are they going to be able to see it and shoot it down? Because if they can do all of that, then you might as well stop. And that is really where we're headed next. We're going to go out and do some flying lessons and take a look at some land and see what happens on the topic of visibility. Okay. And as I thought about this, I said, well, the problem we get into with aeronautics is nothing is ever what you think. There you are on this road. There it is. You just shoot at it. It doesn't hurt you. It's a failure. I thought, well, it's going to be at 7,000 feet in the air, and it's only 4 feet long. So what can people see? I mean, is that like, oh, this doesn't scare us. And there's all sorts of ways to generate an opinion in your head of what you think, particularly the human body, the human eye has such a capacity to see stuff and bring it into a focus where you clearly can see it. And I thought we better look at something that's 33 inches wide and 4 feet long and is 7,000 feet away. Why don't we just explore a little bit? What is that really going to look like? So I thought, okay, I'm not real sure how this is going to work exactly. And I thought, well, let's go to the Grand Canyon and see what 7,000 feet looks like. And I wanted to get something that would give a feeling of scale so that you know where 7,000 feet is. My thought process was if you could have something like a mountain that was 7,000 feet higher than the plane, then if you were on the plane looking up at the mountain, you would understand what 7,000 feet looks like. And I was going to do this in the Grand Canyon, but Google Earth seemed unhappy about showing me the Grand Canyon, so I decided not to do that and went nearby and looked around and found this Gunnison Telluride. Gunnison is a national park around in here somewhere. Gunnison National Park, and you can see there's these mountain peaks, or no, they're not really mountains, they're just high hills. All right. Well, I had to get some rearrangements here. There's the Grand Canyon. When I did this before, I could not get Google Earth to show me the Grand Canyon. I don't know why. But it wouldn't. You can see down here, we got the longitude and the latitude and the elevation of the ground. It's not the elevation. The eyeball elevation is 1,300 miles. The ground itself right here is 1,200 feet. Okay? And since Google Earth would not show me the Grand Canyon that day, I decided to go somewhere else. And I found this Gunnison National Park. And what I wanted to do, one of the things that Google Earth has is Google will take its little car and drive along, and the car has a camera in it. Here is Gunnison. And the camera does a street view version of the view. So, for example, we can take the little street view. Okay, so we can look and see that this is showing to be 11,000 feet in the air, and this is 9,000 feet. So someone here, 8,000 feet, 9,000 feet, would be looking up at something that's 3,000 feet higher than this. So even though it's 11,000 feet, it's only 3,000 feet higher than this. So we can take the little street view guy and put him right here. And there he is, or she is. There's some cars. There's those mountains. So that's what something that's 3,000 feet in the air looks like. Okay, and so we're going to exit our street view. And we will now go to a place that I found that is very specific for, and what is special about this place? Nothing. Blanca, Fort Garland, U.S. Highway 160. These are some farmers down in here. You know, I don't really know what they're doing down in here, but I'm not. There's nothing about this other than it helps me to demonstrate what I wanted to show you. And you can see here that this elevation is almost 14,000 feet right there. And this elevation is 8,000 feet. So if you were standing here looking up at this, you would be looking up at something that's 7,000 feet in the air. And that helps to get a feeling for what 7,000 feet looks like. So let's take our little guy and we'll put him down here. In the middle of, I mean, I just can't comprehend what it is that this is. I'm sure it's very important to the people who live here, and I'm not making any remarks about them. I'm just saying there it is. And we'll roll along here with Google Earth allowing us to come up to our pin. And I'm not a real great Google Earth giant here. Whoa. And so if you were here on this road at this place right here, you're looking up 7,000 feet in the air because you're at 8,000 or 7,000 feet, and this is 14,000 feet. So if you're standing here looking at this mountain, that altitude is 7,000 feet. And it happens to be, in addition, and Google Earth gives you the ability, again, I'm not very familiar with Google Earth. But you can do what Google calls a 3D path, which is a straight path. So we can go from the top of this mountain down to here. And that is 4 miles. So that is a flying distance of 4 miles, which means that this person, this little guy right here, that guy, is 4 miles from there. And this is 7,000 feet higher in the air than is this, at least sort of. And the last thing that Google allows you to do, if you want to, is you can line this all up like we did with our little street view guy. Here we go back into the, I mean, it almost looks like a path. It doesn't even look like a road. But Google Earth will allow you to take a picture. So let's take that picture and we can do some interesting things with that. Okay, welcome back everybody. I tell you, this is going to be, I think, just scientifically, it's just one of those things where they say it's true, but I'm having trouble believing it. I should mention that we went to Gunnison, at least on Google Earth. Gunnison, I think, is near to the Air Force Academy. I think it would be a lot of fun for this video to go to the military academies, the Army and the Navy and the Air Force, just for the cadets to look at it, because boy, I think creating this smart mortar would be one interesting deal for the cadets, even just as a learning experience. And I think some of the Air Force guys could get in a car and go on out to this mountain here at Gunnison and take a model and fly it. Like I said, I'm kind of keeping a secret what the discovery was for a number of reasons, but mostly because as a scientist, I'm just having trouble believing it. Anyway, let's see what we see here. First of all, we went into Google Earth, and Google Earth allows us to line up whatever photograph we want to line up, and from whatever altitude we want to be at. And here is that peak that's at 13,699 feet. And this little place here where the guy is standing is 8,136 feet. So 13,699 minus 8,136 equals 5,500 feet. So if you're standing here and looking up, you're getting an elevation of 5,500 feet, which means that the Smart Mortar, which gets all the way up to 7,400 feet, is going to be up in here somewhere. And one thing I can say is that, you know, from a physics viewpoint, this part of this image is what we call, I think, flatland, the horizontal part. And this part of this image going this way is the vertical part. So we can actually cut this image in half. And it allows us to put it into the 3D drawing program. This is not perfection level imagery, but you'll see what happens. So I went and cut it. And this is nothing more than the flat horizontal portion of the picture now existing as a horizontal plane. And this is the vertical portion of the picture now existing as a vertical plane. And I put sea level at zero feet. And if you go up from there to here, you get to 8156. And so that little guy at Gunnison was standing at 8156 feet. So we now have this as 8156 feet, and we happen to notice that that peak was 13,699 feet. And so this distance from here to here, again, using SketchUp does all this data for you, but if you go up to here, we've gone up 5,531 feet. But if you go down here to sea level and go up, it's 13,684 or whatever. I mean, it's at that level that is at. And so the mortar itself flies along at 7,253 feet. But again, that's going to be 7,253 feet above this ground level down here. So if the Smart Mortar was flying around, it would be right up in here. And the other thing I wanted you to see, from here to there is 4 miles. So that's the range that this Smart Mortar flies through. And one of the limitations of the 3D drawing program is that it just creates a space of how much space it's drawing in. And if you get little tiny things inside of great big spaces, it gets where it won't show them. That's how it is. And I got these lines in here for no reason other than to just show me where I'm supposed to be looking. But if we come zooming in here, you can see that now I have a little trouble drawing humans because they're such rounded organic shapes. And I've got these little mannequins here sitting in as observers. And I'm going to go and I'll show you what they look like. I can't get much closer than this to them in this view that has a panorama as big as this in it. Okay, so this is the two little mannequins, and they are my representation of a human from the top of his head to the bottom of his foot is 6 feet. So he's 6 feet tall. He's got a head and face, eyes. One guy's sitting here, and they're sort of sitting on this little platform right here, and they're looking over to see the Smart Mortar flying around. And this I can show you at great detail because this is the only thing in this picture. But when we take this little image and put it inside of that other image, SketchUp just gets all mixed up. And we'll go back to that in a minute, and we'll show you some other things. All right. Hello again. So we're looking. We got these two little guys. We've told them, you know, this is a military setting. We could, if we wanted to, say, all right, these are enemy people. And their boss, they're all over here, this crowd eating lunch, and they sent these two guys over to watch for the Smart Mortars, because you never know when those Americans are going to send a Smart Mortar against you. And so the big group of 6 or 7, 8 people and the 3 or 4 trucks, they're sitting over here eating lunch. These two guys are supposed to be watching for the Smart Mortar. Just keep that imagery in your head. And just one more time, we will zoom in to the situation that these two guys find themselves in, where they're sitting in their chair. And I just remember this line says where they are. So to try to get some image of what they're going to be seeing, it kind of looks like this. This green line is something to do with Google. I think it marks where the county line is. I don't really know what it is, but it's a green line that was put in there by Google. It's not on these mountain peaks. I don't think that's snow. I think it's just sand. But there they are. These guys are over here eating. They're watching because the Americans are up here and they have this mortar and they can launch it. And of course, this could be completely flat land where the Americans are over here somewhere. I just wanted to give you something that you could look at that was 7,000 feet tall. And this is 5,500 feet tall. So if the Smart Mortar was up there, it would be up here. And of course, I guess they're going to be eating their sandwiches too, because they don't see anything. And if you had a pneumatic cannon down there firing off the Smart Mortar, I don't think you're going to hear it at a distance of 4 miles. But they're looking. And the question that comes up is, what are they going to see? And actually, the issue of seeing things in the military has been around for a long, long time, because prior to GPS and satellites and eyes in the sky and radar, you know, particularly on the ocean, if the captain said, hey, look, are there any boats around here that could be shooting at us? The guys would look back at him and say, well, no, we don't think so. And he'd go, well, how come, well, why are you saying that to me? And they'll say, well, just because. And the other thing is, we got some guys looking around outside of the boat and we didn't see anything. So looking around to see what you see is something that's been in the military for a long time. And remember, we're talking about a group of 30 or 40 American soldiers in an outpost, and they're trying to keep themselves safe. So they're not up against a ultra technological force that has everything a force could ever have. It doesn't have radar. It doesn't have access to satellites. It doesn't have drones with FLIR. It doesn't have any of that. It's just guys with trucks and some AK-47s, and they're like messing around with the Americans, and the Americans are trying to keep them from bothering them. And they have this Smart Mortar that they can use. And the Americans said, you know, if you guys come over here and mess around with us and get within 4 miles of us, we're going to send one out there on you. Just let you know that. And they're like, well, okay, but we're going to sit here and look and watch. And if something starts happening, then we're going to do something about it. And the Americans will say, okay, let's see what happens. But this has now devolved itself back into a situation of looking around to see what you can see. And the question is, well, what is it that you can see when you're looking around? And what I've arranged for you here is, you know, going down the primrose path. and let's just look at some stuff. This is a military dynamic research 1991 final report, public distribution, Air Force Systems Command, just identifying it. They went and discussed when people are looking for something. This is this guy Johnson, and said, well, how can we scientifically discuss looking for things? And he said, well, I'm going to divide it from the very beginning where you don't see anything to the situation where you might see something, to the situation where, yeah, I know I'm seeing something here, to the situation of I've seen something and I know what it is. So he went from detection, I can see something, orientation, this object is symmetric or not, and it's either more vertical than horizontal or more horizontal than vertical. Recognition, it's probably something like a truck or a house or an aircraft carrier, to I know what this is. And here is a visual and these Johnson criteria were the way that this military guy, and it was the way it all started. It's now been turned over into a big issue with night vision goggles and cameras and detection of human beings with non-human video visual devices. But it's all the same stuff. Here is, yeah, there's something there. I think what I'm seeing is a human being. It's a fireman. That's what they're showing here. And what Johnson came up with, and it has to do with the resolution of the human eye. Resolution in seeing is what is the level where you can distinguish between two things. And the actual way that resolution works is it's related to an angle, the angle of what the object subtends as your eye views it. Because, for example, a human hair, you can see a human hair in someone's fingers if he was holding it up. But if he started walking backwards, you wouldn't be able to see it. Even though you can see a human hair, if he gets far enough away, you can't see it. And the same thing like a Chevrolet Suburban driving away from you on a highway. It's a car. It's a big old car. But you know, if it gets far enough down that highway, you are not going to be able to tell if you are seeing it or not. And so what they discovered was, with respect to seeing things, you have to put in this angle that it subtends. And the angle that a human eye can resolve is about 1 arc minute, or a line pair. And what Johnson discovered was that the difference between seeing something to say, I think there's something there, to it's taller than it is wide, to it's a human, it's not a house, to it's a fireman, or it's a lady with her child. You need more and more line pairs or more arc minutes of resolution to go from not seeing anything to being able to identify what you're looking at. And the other thing I wanted to show is they looked into the issue of what happens with respect to recognizing something when it has a dimension where the height of it is wider than the width, or the width of it is wider than the height. And these are just some aspect ratios of different things. But what they're showing is it still is 2 or 3 or 4 arc minutes or line pairs. Remember, the line pair for humans is 1 arc minute. Line pairs are more related to video equipment, and arc minutes are more related to living structures, but they're both the same thing. It's 3 to 4 arc minutes is what you need to recognize what you're looking at. And so let's take a look at that and see what that tells us. Okay, and welcome back again. This gets stranger and stranger. We're on the primrose path here. That way is what we were looking at. This way is what we've talked about. Let's take a look at the little Smart Mortar. I had some drawings where I had a simple representation of the Smart Mortar, and I was hoping to make one that looked like this because I think it'd be easier to get this to go down a pneumatic cannon. But from an aerodynamic calculation program, this will fly and work. And I don't know what this will do. So it really got turned into this. But we can look at some things. Unaided, not binoculars, unaided human eye, best resolution, something is present. That's just recognition, 1 arc minute. Best resolution for it is taller than it is wide or is wider than it is tall is 2 arc minutes. So now we have to look at this resolution of the angle that the object subtends in your eye. And as you can see, the little Smart Mortar, I mean, it's pretty, it's aerodynamic. I mean, I have a problem with it in the sense that I really think this is pretty, and I can't tell if I think it's pretty because I created it or because it's pretty. It's just neat. And if you look at military flying things, particularly flying things that have been around a long time and were very successful, they're pretty and they look like birds. My son said this looks like the peregrine falcon when it's pulling itself into its dive. But that's a digression. Okay. So we have to come up with an opinion of, well, how big is this thing? And it's a dimension, so you can't take all these curves and give it a dimension. And this box is showing that it's 18 inches long by 33 inches wide in the bulk of its dimension. Remember now, at some point this thing is going to be pointing its nose down and diving down at the people. And when they're looking at it this way, it's 7 inches tall by 33 inches wide. So, using the aeronautics program, we took it, and this board here is a board that has the dimensions of what our order of magnitude is. So if we go up here, we're at 7,200 feet. Okay, and if we go over here, from here to here, so we'll mark this, and we'll mark that, and that is 21,000 feet, which is 4 miles. And this is the beginning of some of the weird stuff. You may be saying, well, what is the point of this arrow? And it's because, well, why don't we just look at the Smart Mortar? And I'm like, okay, let's look at the Smart Mortar. Well, is there one in there? I mean, this one's in here, but this one is a demo Smart Mortar to show us, because this one happens to be 1,026 feet long. Now, I don't know. I just don't know. I have a feeling that there are pilots who are like, oh yeah, you're running into the pilot thing, which is nothing is what you think it is when you get into the three-dimensional space and you're miles in the air. But it's okay. We'll go look around. And we're like, why can't we talk about the real mortar, the Smart Mortar, the one that's flying around? And I'm like, well, okay, we probably could. Oh, wait, what did we just see there? What was that? Oh my, there it is. There's the Smart Mortar. And you can see, once again, this computer system can hardly show something as small as that Smart Mortar if it's placed against the scale of the spaces that we're working in. There it is. There's that 18 by 36 right there. And of course, the other thing that we're looking at is the glide angle, and it goes from here to here. This is 100 feet, and this is 854 feet. So that's a glide angle of 8.54. So we took it from our pneumatic cannon and we shot it straight up. And the way we got it to go straight up is we kept adjusting the angle of attack so that it has no lift because you have to remember, if the Smart Mortar, we'll take this Smart Mortar, if it's a flying device, then the lift that it generates is that way when it's going straight up. So if you don't get the lift to be zero when you launch it out of the cannon, it's going to go up in the air and come down and land right back on top of your own soldiers, because the lift is directed that way. So the lift pulls it over and it comes around and it lands on you. So you have to keep adjusting the angle of attack of this device so it has no net lift, because the lift is not lift up, it's lift sideways. But if you do that, it goes up 7,280 feet or whatever it is. And at that point, it is now at 163 feet per minute. And you take, again, you take the nose down. So when you do that nose down maneuver, it's important to understand that it is pointed straight up. So when remember, you're not actually talking to it. This is a fire and forget weapon. The inner programming says do a nose pitch down maneuver. So when it does a nose pitch down maneuver, it brings itself to almost horizontal flight, a little bit of nose down because it's gliding on its glide slope. So it pitched its nose down, but that didn't make it point at the ground. It made it into level flight because it was pointed straight up when it did its pitch nose down maneuver. Weird stuff. So now it's flying along. And remember, we got these guys down here eating their chicken sandwiches, looking into space, watching for that. And again, there may be pilots and other military observer types who are like, I know what you're getting ready to do here. But let's go ahead and use our arc minutes and see what happens. The resolution is 1 arc minute. That's just saying it's there. 96,257 inches. Is 8,000 feet. So if it's 28 inches across, a human being will not see it if it's more than 8,000 feet away. They won't see it at all. And if it's 33 inches across, they won't see it at 9,000 feet. So that circle happens to be 9,000 feet. And you're like, so what? But I'm telling you, you gotta think like a pilot, because what did we happen to sit down here just for the purpose of scale? Uh-oh. Here's our two guys eating their chicken sandwich again. And these two guys have been given the job of watching for that Smart Mortar. And again, it's so big that when I turn this and get this tiny little image of them looking up there to see that Smart Mortar, the question is, where is it? And the answer is, if it's beyond 9,600 feet, they're not going to see it at all, which is just crazy. And if you convert it over to pointing straight on at them, the arc minutes for 7 to 8 inches gives a distance of about 1,000 feet to 2,000 feet of when they're going to see it, which means if it flies along like this, at right here, if it points its nose down at them, they're not going to see it until it's 1,000 feet away from them. And that's just like, this can't be true. But we can explore a few more things and see if we really believe that. And that's our next discussion point. Okay. And again, welcome back, everybody. So here is, from a scale viewpoint, this mortar would be like, well, that was 1,000 feet. So this would be 6,000 or 7,000 feet across if this was that. But this is expanded. This is the real scale of real feet. And what I wanted you to look at was this computing program that's available on the internet. It's just a calculator. And what happens is, with the way the human eye resolution works, is it's degrees of arc that subtend the retina of the eye in order for the eye to be able to see it. And we've got this distinction between, it has enough effect on the eye that you can say, I think there's something there. And then if you get more a larger portion of the retina impacted by the image, instead of 1 arc minute, 2 arc minutes, you can say, well, I think it's taller than it is wide. And if you let it subtend 4 arc minutes, you can identify what it is. And the way this is the size of what you're looking at. This is how far away it is. And this is the angle that it's subtending. There's the angle there. That's 1/2 of the angle. And so if you happen to know the value of 2, so they have angle, distance, and size. If you know 2 of these, you can get the third one. And the critical thing to remember is, whatever distance or size you use, the value of the units for the size has to be the same value as the value of the units for the distance. And again, if we go back over here and we look at recognition, identification here, there look 5, 6, 7, 8 arc minutes. Remember, the 1 line pair for a human is an arc minute. So this is 6 or 7 arc minutes. Recognition is 4. And even with items that are wider than they are tall, it's still 2 to 3 arc minutes. And the question that comes up is, one of the things I was addressing is that if this Smart Mortar is flying along at an angle and the human beings are looking at it this way, they're not actually going to be seeing the entire length of this Smart Mortar on its real dimension, because if we, for example, if we put one here and one here, okay, you can see that this distance from here to here is 4,000 feet. But if you put a protractor on this one and bring it down to 90 degrees, then this distance is 1,600 feet. And so if your observers are far enough away from the Smart Mortar, they're really seeing this distance, not that distance. I have a feeling probably it doesn't matter. It's just something to remember, which is why I was putting out distances here on this board for 28 inches, because if you calculate it out, this 33-inch Smart Mortar becomes 28 inches. But let's just leave it at 33 inches. And the question is, remember, 1 line pair or 1 arc minute is when this structure begins to be where a human being can't tell if it's there or not. So will you, even though this is wider than it is tall, we'll just use this large dimension. As I looked at the research, I could not get them to answer if it's wider than it is tall. What dimension are you supposed to use? Are you supposed to use the diagonal? Are you supposed to use the square inches and convert it to a square? What number are you supposed to use? But we'll just use 33 inches. Okay, and I've actually turned it on. And remember the size of it. Let's calculate for what is the distance where the human being will not be able to see it. So we want to solve for distance. The angles that we're using are arc minutes. So 1 arc minute. The size is 33 inches. What is the distance? And this is 113,450 inches. Which is 9,454 feet. That's 1 arc minute. So at 9,454 feet, this 36-inch wide structure, a human being would not be able to see it. And I thought that I would just give you a demo of that. And we run into the issue of, with scale, it's difficult for the computer to show you little things compared to big things. So I went, here's our little guys. They're the guys that look to see if they can see anything. These are some guys that are going to help us. I asked them if they would do an experiment with us, and they said, okay. This is my mannequins. They're pushing the wagon. This guy's driving it. This guy's pushing it. This guy is holding up the Smart Mortar. And the those mannequins are 6 feet tall. So this whole structure from here to here is 9 feet. So it's 9 feet tall. But remember, this little mortar is only 36 inches across. So we can now ask these guys if they would take this and go out onto that road there near Gunnison and push this cart along, and the guy that's holding up the Smart Mortar will hold it up and then put it down, and hold it up for a while and put it down. And we're going to see if you're able to see it. So that's our experiment. And so again, I'm going to start this battle with the SketchUp program. Here's our roadway. This is 4 miles from here to here. This distance from here to here is about 4 miles. And we're gonna we went down in here and we put this little cart here, put it on that road, and we said start pushing, and we're going to have these guys look at it and see when it turns out that they can't tell if he's holding up the Smart Mortar or not. That would be 1 arc minute. 2 to 3 arc minutes is where they would be able to say, is he holding up a trash can lid or is he holding up the Smart Mortar? And that's 9,000 feet. And the problem that you get into with this program is that it really is not able, it's just the program. 9,000 feet 9,000, that's 6,000, 8,000, 9,000. There's 98. So there's 92. So right here, if these guys took if these guys took this little cart and pushed it down this road at 9,400 feet, you would not be able to tell if they were showing you the Smart Mortar or not. You just wouldn't know. And again, you can see that the distance to the mountain is 19,000 feet. So right here, it's gone. They're pushing down this road, and you have no idea if they're showing you the Smart Mortar or not. And it's just, that's pretty weird. All right, let's see what else this means. Okay, and hello again. Welcome back, everybody. So we're looking at the profile of this flying Smart Mortar. We have a little complexity when you're looking at it dead on. This is 7 to 8 inches, and that's 33 inches. And again, I'm not completely sure what distance you're supposed to use. Now, this is when it's coming down at you. You want to know that it's the Smart Mortar so you can make a decision about what are you going to do. I don't know that it should be 7 inches. It seems like it's hard to say it would be 33 inches. Let's just, like I said, I couldn't find in the research how you're supposed to do that. But remember, with the battleships and the 12-to-1 angulation or 12-to-1 length to width ratios, they were using 3 arc minutes. So let's just take 33 inches and use 3 arc minutes and see what happens. And we took 33 inches and we put our 3 arc minutes in here and we calculated the distance. And that comes to 37,815 inches. So 3,000 feet, 3,100 feet. And I think that's conservative. But what that means is you can go here and put your distance measuring at the level of this guy's head and go out here and right here at there's your 3,000 feet. So if this thing, here is where it became invisible because they're looking at it flat on. So if it turned itself, when it came down at them, they wouldn't see it until it was right here. And one of the things that happens when it's not on its glide angle is that there isn't a balance of forces. There is extra force left over from gravity to pull on it, so that when you take a flying object off of its glide angle and point it down, it begins to accelerate, and it will continue to accelerate. The magnitude of the acceleration depends upon how much gravity force is left over to pull down on it. And it only stops accelerating when it hits the ground or when the drag from its velocity is equal to the excess gravitational force. And so it gets up to about 200 or 300 miles an hour. It was at 100 miles an hour. Now it's at 300 miles an hour. And 88 feet per second is 60 miles an hour. So 300 miles an hour divided by 60 is 5 times 88 is 440 feet per second. So 3,115 feet divided by 440 is 7 seconds. So when they finally see it, they will have 7 seconds to make up their mind what they're going to do about this. That is not much time. And one of the things we looked at is, well, what would happen if they started running? They went, oh my gosh, this thing is coming at us. And this is nothing more than Google. Running speed, 6 miles per hour. 6 miles per hour is 1/10 of 60 miles an hour. So 60 miles an hour is 88 feet per second. So 6 miles an hour is 8 feet per second, 8.8 feet per second. So 8.8 times 7. So if they saw this thing and turned around and ran, they would get 61 feet before it hit the ground and blew up. And it's carrying 4 pounds of C4 and configured to create shrapnel. I don't know that you would be safe from 4 pounds of C4 at 61 feet. And this includes that they immediately figured out what they were seeing when they saw it, which I don't even think would happen. I think when they saw it at 7 seconds, it would take a second or two for them to say, oh my, that is one of those smart mortar things. We need to get out of here. So now it's more like 5 seconds. And that's 40 feet, which just, they're not going to be able to run away from it. And this is one of those conclusions where you're just saying to yourself, whoa. Because what it means is the smart mortar is invisible, will never be noticed. The only way you'll see it is if you happen to be looking directly at exactly where it's coming at you from. And once you see that, you have somewhere between 5 to 7 seconds to do something, which I think it really is just not going to happen. That's weird. That's not what I thought the answer was going to be. All right, we can look at a couple of other things, mostly related to people saying, oh, come on, I just don't buy it. So let's go look at something else that is in the same topic area. Okay, and hello again. Welcome back, everybody. As I said, we're going down the primrose path. Let's go see what's down this way. Again, performance ground observers. This is the military, 1966. They're still tangled up in this business of seeing things in the air, flying along, and trying to figure out how do human beings do that? What is their response? What can they see? What can they not see? How do they identify stuff? This comes extremely close to what we're talking about here, because these are flying objects in the air and they're working through what is the science of all of this. And I could spend hours going over a research, but I'm not going to. Range, propeller, helicopter. Okay, this is the chance that they saw it. These are different flying devices. The U-1A is seen sooner, but it's bigger. The one we decided to look at is this U-6A, which is an airplane. And for some reason known only to the military, a company makes a product and then the military gives it 7 or 8 different names, which is fine. I don't mind. I think it has different uses in the military, but it can get a little confusing. So let's look at this. This is a helicopter. This is the U-6A, a flying airplane, propeller-driven airplane. And the reason we picked the propeller is because if you read the study, the propellers were going about 100 knots, which is 111 miles an hour, which is 163 feet per second. So it's about what we're doing. And they're flying things in the air, flying along that the soldiers are looking at. And the U-6A, the 50% point, is right around 8,000 or 9,000 meters. Okay? Maybe 8,500 meters. And that is essentially 25,000 feet, 4.8 miles. So they see this airplane at 4.8 miles. And let's look at some other values. This, by the way, was just that same deal. Here we go again, detecting it. I think I see something. This is, well, I know what it is. And again, the O1A at the 50% level is 5,000 meters. And we have this calculator by Unicon. This is such a cool calculator. It prevents you from making stupid mistakes. All right, so we're looking at length. O1A, 50%. 5,000 meters. So let's convert meters. This is so great. Well, it's so great if you're like me and manage to constantly confuse yourself. Meters to nautical standard miles, I think. Okay. That's not right. All right, sorry, I got it straight. So a mile, parentheses, S, is the miles we're talking about. So now let's convert meters into standard miles. And this, I'm sorry, it was 5,000 meters. And this is the exact relationship that we've been talking about the whole time, which is the difference between 4 to 5 miles, I think I see something out there, and 3 miles recognition. Oh, that's an airplane. All right, so let's see what else we found. Positive recognition, where they really did get exactly right what it is. There's our O1A, which is down in through here, and that's at 3,000 meters. And then some other stuff in this study. I've been telling you the whole time, anytime you get into flying and aeronautics and people who are not pilots in the air doing this and that, everything is so weird. Here is where they said, well, you figure out what this is and don't use binoculars. You figure out what this is. If you think you see something, pick up your binoculars and take a look. This is, you can do whatever you want. You can look around, or you can use your binoculars to look around. You use them when you want to, or you can use them all the time. They, of course, scientists are always looking for statistically significant stuff. But the truth is, looking at this, there's hardly any difference in these curves. It's crazy. Here you can see this is the one they thought was significant, where you're using the binoculars all the time. The 50% is 9,000 meters. And the no binoculars is 8,000 meters. So what? 8 or 9, here's 8, this is 9, so 8,500 versus maybe 10, 2,000, 6,000 feet That's all that the binoculars give you. So when you say, oh, yeah, but they're going to see the Smart Mortar and they're going to have binoculars and they're going to know what's going on, and everything that you've been saying is completely not true, well, there you go. Here's the study. And here's some airplanes that we made. All right, let's, just in case, I know that you may be saying, what was this experiment exactly? So here's where they had one group. Here's where they had some other groups. And the planes would be brought out and come around and fly down a pathway, on this line versus that line versus that line. They were trying to see if it made much of a difference if you were flying into the sun or away from the sun or towards the sun. And then they were also looking at if it was flying directly at you as opposed to you looking at it off from an angle. And scientifically, there wasn't much difference on that off-angle viewing. That also was a little surprise to me. But that's what they would do. They put these people out here. They would have the planes take off from somewhere, and they would fly down and get lined up, and then they would go down this flight path, and these people would say, or work to say, to try to figure out what is it that they're seeing. So that's interesting. Now you might go, well, now that's very close to what we're talking about with a Smart Mortar, but what were they looking at? They weren't looking at something that's 33 inches in size. And according to all of the science, it doesn't much matter that it's 33 inches in size. That a 300-inch item is just seen 100 times further away than a 3-inch item. It's all an angle of view. So let's go see if that came out to be about what the science of vision would say that is supposed to happen. Okay, and welcome back again. As I said, I'm not a military pilot. I keep getting this mixed up. The one we're thinking about is the U-6A. So the U-6A was detected at 9,000 meters at the 50% level. The U-6A was recognized at the 50% level at 5,500 meters. And the U-6A was positively identified at 3,000 meters. Okay. I thought, well, that's interesting. What does that mean? And I went out to the internet and just wandered around trying to it turns out the U-6, U-1, all of those are designations of airplanes by the military when the military purchased an airplane and made it a military airplane because they just declared it to be a military airplane. But it was actually made by de Havilland, and the U-6A is one of the de Havilland planes. And I thought, okay, I will go into the internet. I will find some drawings of this de Havilland plane, the U-6A, and create a model of it. And this is the model I created, and I here am having it as a bright yellow so you can see it. And I've superimposed the model that I created on these drawings, and you just have to take my word for it. These are drawings of the, I think it's the DHC3, but it's the U-6A, de Havilland U-6A. And, you know, I got the wheels and the struts and the wings and the flight surfaces and the profile and the propeller. And this is all a three-dimensional structure. Then I went and found one. There's people, a lot of history of flying is involved, particularly, probably even now, but boy, in the past, There's plenty of pictures of these planes. These planes are definitely connected to the military. And that's the color scheme. So I went and tried to make for myself the color scheme of that airplane. And this distance, I think this is to scale. It might be. I may have magnified it. Let's see here. We got to turn this. Okay, that's feet. So the problem that you get into with trying to show all this stuff is, that's 12,000 feet. So in order for it to be big enough to see it, it has to be gigantic. And you don't get it to the right size until you start working with it inside the drawings. That doesn't mean anything. It's just, once again, confusing. But this, I believe, if I remember correctly, see, now we're into the fact that we can't display the real size in this drawing because we have these gigantic drawings also in the picture. So this can be fixed. Okay, and so these are really the exact same pictures, but they're being shown by themselves in a drawing where the gigantic pictures of that landscape are not there. And you can see that I've tried pretty hard to have this plane, so that's 47.9 feet, to have this plane that I've drawn to be, and this is 47.6 feet. So this little yellow plane that I've created is as best as I can do. I mean, other than spending a year working on it, to create a model of the de Havilland DHC-2 Beaver, which was the military U-6B. And there's the colors I picked for it. And then I thought I would show you, there it is flying along, and here's a little Smart Mortar down under it to give you some feeling for a comparison of the size of the Smart Mortar to the size of this airplane. And here I blew up the Smart Mortar. It's about 8 times, it needs to be 8 to 9 times bigger. But the science says you don't have to do it that way. That, you do it by minutes of arc. And so here we have it for us to visualize. And let's go back over to those big size pictures and see what we see. All right, and we're back at the Primrose Path, and here are these gigantic versions of this airplane. And here is the mountains. And here is sea level. And here is 8,136 feet above sea level. So now the mountain is 13,600 feet like it's supposed to be. And we have our little guys down here. And as usual, again, we have this terrible fight with trying to find our little people because they're so small compared to this image. But there they are. And they're looking up at the mountain. And remember, we're trying to say that they would see something flying up there. And this distance from here to here is about 4 miles. And look, there is something up there. And I put it in here for you, and there is that airplane. That's 30 feet. That's 33 inches. And 30 feet. You can see that they are just barely simply even just seeing that airplane. There it is. From their vantage point 4 miles out, there's the airplane. And if I took the airplane out of that picture, you can see from a scale viewpoint, you would never see that Smart Mortar. And I put in here some distances just to help you convince yourself, but that's 4 miles. So that's 4 miles. There's these little tiny guys here. Okay. Looking out over this land to see these, there they are. And 4 miles away from them, across this land and up to the top of this mountain area at 7,000 feet in the air, is this airplane. And next to the airplane is this Smart Mortar. And this is the best I can do to demonstrate to you that they're not going to see the Smart Mortar at all. They're not going to see it, which is wild. And I've actually been hiding from you in these drawings, and it's even hard for me to do it, but somewhere up in here is the Smart Mortar. This is a Smart Mortar up there in the picture when the airplane is not there to help find it. And I can't even find it. It's in here somewhere. But I'm trying to give you a demonstration that the Smart Mortar is just completely and totally invisible to these people. This picture is the same as that picture. And the other thing I did is this picture. Okay, back in here, there's the Smart Mortar right there. Right there. So there is where it is, up here at the top of the mountain. That's what I couldn't find before, but there it is. And this point here at this cross mark, there's another Smart Mortar right here. That's that little dot right there. That is the place in this profile where the Smart Mortar would begin its downward flight. Right there. And if you go down here and get yourself in the position of these guys and have them looking up at that place in the sky where that crossover occurs, they're not going to see that Smart Mortar at all. And it's just amazing. So that gives us the ability to continue to work on the Smart Mortar. There's a lot of aeronautics that I can talk about, and that's a whole separate set of lectures. But what it means is it's okay that the Smart Mortar goes 7,400 feet in the air, turns itself into horizontal flight, and flies over to land on the enemy forces. They will never see it. They clearly are not going to hear it because it doesn't make any noise. And that, I think, makes it a significant weapon. It is my hope that it's enough of a significant weapon that what will happen is people will just decide that if the military wants to own this 4 miles worth of space, 4 mile diameter circle of space, that the enemy forces just won't be there because they're going to be but since it has flight control surfaces and can fly and compensate and keep up with where it is and land where or impact where it's supposed to, it means that the U.S. forces can just put these wherever they want to, which means that the enemy forces will constantly have this thing landing on them that makes no sound that it arrives when the American forces feel like sending it. It's 4 pounds of C4 plus shrapnel. And they have no idea when the Americans are going to launch it, and they have no idea if it's coming. And they're not going to be able to see it or detect it. And if they maybe, I mean, it's all a lot of curves. I don't know if it would reflect radar or not, but that's a very sophisticated radar installation to pick up that smart mortar. And if they're broadcasting that kind of radar energy, there's all sorts of radar seeking missiles that will just take out their radar facility. So I think we can say that it's okay that the smart mortar, based on aeronautics, has this flight profile. And I'll do another set of lectures on the aeronautics of it all. And again, we'll say, boy, do I think the military academy cadets would get a kick out of this. They would get a kick out of making it and flying it and really working through whether something with this capability has any military application. I think it does, but that's not really my area of expertise. All right, and here we go. I have to bring to your attention that I keep getting myself mixed up about the planes. So this is detection of the U-6A, detection at 8,500 meters. Okay. Tentative recognition U-6A at maybe 5,500 meters. Okay, so U-6A, 5,500 meters. And here is the U-6A where we're attempting to get a size value, 30 feet and 4 inches, which is 30 feet is 360 inches. So 30 feet and 4 inches is 364 inches. So tentative U-6A, 5,500 meters, identified 364 inches. So now 5,500 meters is 216,535 inches. So 216,535 inches compared against 364 inches worth of size comes out to 5.7 arc minutes, which is precisely what we've been saying all along in this exact scientific study, where they really used real stuff and real people, where tentative recognition should have been at 3, maybe 4, at 3, maybe 3.5 arc minutes. When it got applied to the actual real world with real items flying around in the sky and people looking at it, it turns out that it was 5.7 arc minutes. And what we've been doing with the Smart Mortar has been keeping it at 2 to 3 arc minutes, which is way tighter than what the real actual science showed with actually real flying things flying in the air. And what that means is, in terms of the Smart Mortar being non-visualized, not perceived, and probably not even that you can see it if you tried to see it, you're just normal people in the absence of very sophisticated technology. They're not going to see it. They're not going to see it after it takes off. They're not going to see it when it levels off. They're not going to see it while it's flying. And they're not going to see it when it comes in on them until it's so close that they can't do anything about it. And if they have people out in the fields as spies watching for smart mortars, those people aren't going to see them at all. They will notice and hear that the pneumatic cannon fired off a smart mortar, but then other than that, they will have no knowledge about it at all. They won't see it. They won't know where it went. They won't know what point of the compass it's flying on. They won't know anything. It's very interesting.